is rotated. Okay. Let's. Can everybody hear me? Octavio?
Yes, we can hear you.
Sorry, can you repeat? My volume was low.
Yes, we can hear you.
Good. Okay. Sorry for the delay. Let's start. Today I tried to. I uploaded, unfortunately, a very last moment the slides of today. I will try to write on the slides with a tablet to slow down the pace. Let's do these experiments. Otherwise, I will go back to the previous way of teaching. And let's see. Now I try to share. Okay. Good. Can you see this?
Yes, I can see the slide.
Okay, nice. Yeah. So the lecture of today it's on as you could see from the let's use this one that is better on a mouse. Okay, good. So we start. First of all, hope you had a nice holiday, Easter holiday, and this batch of lectures it's on kinematics, direct kinematics for robots, and we first before defining kinematics for a manipulator or a articulated robot, we need to define the kinematics of a rigid body. And before to define the kinematics of a rigid body, we need to be able to define its position and its orientation. And I think it's worth to pay a lot of attention in the way we represent orientations, because there are many ways to represent orientations, and many people can be confused because there are some problems in presenting orientation, while to represent position there is never a big problem. The first way to represent orientation is a rotation matrix. So as I said, a rigid body is a 3D object, and rigid means that the distance between any couple of points remains constant. And a rigid motion, it's what we define the motion of a rigid body in space. So a rigid body is a body that is not deformable, because the relative distance between any of a couple of his points is remaining constant. And manipulators, as I said, there are a serial chain of rigid bodies, which are the links that are connected by the joints. Before starting this lecture, I will do a quick math review on the most important concepts that we will use in the course. Some of them I will introduce later, but these are the ones that are useful for kinematics. And the first concept, it's the concept of vector norm. That is represented by this. Let me see if I can change the pointer. Okay. Okay, so this symbol is the norm symbol, and the norm induces a metric in the vector space. Well, the space is the vector space is the Euclidean space where our position vector, for example, live, and introduces the notion of distance. And the vector norm is a scalar, so it's a number. It's always positive, and represents the magnitude of a vector. So the length, the absolute length of a vector. And there are many kind of norms, and the most famous one that we will use is the Euclidean norm that has this form. So if you have a vector v, the Euclidean norm has a subscript 2 and is the square root of the square of its component. In this case, we have n component because the vector v lives in a space of dimension n, while in the Euclidean space it will be dimension 3. Then, so what a unit vector is, it's a vector that is defined in a space V where there is also defined a norm that has norm 1 or length 1, and is codirectional with the U. So let's say U hat is the unit vector associated to U, and is this formula, which is divided U that carries the information on a direction by the norm. This way, we keep we obtain a vector of length 1 or norm 1 and of the same direction as U. And examples of these unit vectors, for example, are the Cartesian vectors 1, 0, 0, for example, or 0, 1, 0. All these are unit vectors. Okay. Now, the next concept, it's the concept of scalar product. Does anybody of you remember what a scalar product is? You should have studied in physics or in other calculus or math, basically.
The sum of the product of the element of the vectors.
The component of the component-wise product, you could say, yeah, which means that the product between the components is done of the vectors of the two vectors is done for each component separately. So if you have two vectors living in a space Rn, the scalar product between them is defined. This is these three ways that you can define different notations, and one of them is the one that we will use mostly is the notation V transpose U, which means we will project the vector U on the vector V, and the result of this scalar product that again, the output of this is a scalar, so it's a number as a norm, as the same as a norm, is doing the product of each component of the two vectors and summing them together. Intuitively, as I said, is the projection of U onto V. And this is graphically illustrated in the picture below, where you can see here that the vector V is projected onto the vector V. So the vector U is projected onto the vector V. There is an angle between them that they could be parallel, they could be perpendicular, or they could have any angle. And the projection, it's a number. And in this case, is either positive, or in this other case, the projection will be negative number. So it's not like a norm that is always positive. This could be also negative. And and the property of a scalar product is that it's commutative. So I can exchange the order of the two vectors and have the same result. There is an important link with the previous concept of norm, of Euclidean norm. And you remember we were the Euclidean norm defining as squaring the component of the vector and summing them and do the square root. So this is the same if you use the scalar product idea of doing the scalar product of a vector with respect to itself and doing the square root. Okay, is it clear? Because this goes for V1, V1 plus V2, V2 plus Vn, Vn. And finally, in the case of R3, so what we are interested to, there's an important formula to define the scalar product that is equal to the norm of the first vector V times the norm of the second vector U times the cosine of the angle between. And we will use this formula a lot. Everything is clear?
Yes.
Okay. Then the other concept is the cross product or vector product. That is defined as V cross U, the cross product between V and U. And this time, the output of this operation is not a scalar, but is a vector that first is only defined in R3, so in the Euclidean space of dimension 3, and second is orthogonal to the plane defined by U and V, and third, we said that we define the direction. The direction of the vector is defined by the right-hand rule. The right-hand rule, you should have seen it in physics as well. Is quite famous to compute, as we saw the Lorentz force in a coil, and you should align the first vector. This time the order matters. So the first vector with the index finger, second vector as the middle finger, and the cross product or vector product vector will be on the third finger on the thumb. Then we have again a formula that it's very important, and we also use this a lot, and is that a cross product of V times U is equal to the norm of V times the norm of U times the cosine of theta. Okay, what I did wrong here?
It's not the cosine, but the sine of theta.
Yeah, right. Okay, yes, it's sine, correct, because the previous one was for the scalar product. What else? What else is missing?
This is only the norm and not the direction.
Yeah. So the direction, this is only the norm of the or vector. While before it was a scalar, so there was no problem. Then a way to compute the cross product is using this formula. We take the first vector component plus the second vector components, and we multiply. We consider first this this row, and we do the a cross between the elements this way. So U2, U3 minus B3, U2. So this is a minus sign for this part. And then we consider this row, and we take the cross of these two with a minus sign. So do the same thing as before, but with a minus sign in front. And then we take the third row and we do the same thing. We take the third row and we do these two. So is a mnemonic rule to compute it. V2, U1. Okay. Then an important property of cross product is that it can also be written as a product of a matrix with a vector. And what does this mean? We can express this way. So we build a matrix made with the component of the first vector B. We have the third component here, and the second component here, and the first one here. And then we multiply by the second one. And we will use this result very extensively. What do you see in this matrix of strange? There's something peculiar in this matrix. And the things you can see is that there are zeros on the diagonal, and the terms, the off-diagonal terms, are kind of symmetric, like the same ones, but with an opposite sign. So the matrix that has these properties of having zero on the diagonal and the opposite ones about the diagonal and the terms about the diagonal off-diagonal terms opposite is as a name, and it's called a skew symmetric matrix. So a symmetric matrix has the term about the off-diagonal term the same, and a skew symmetric as opposite in this way. And this is a peculiar skew symmetric matrix, a special one that is associated to the cross product. So whenever you have a cross product, you can always define as the multiplication of a skew symmetric matrix times a vector. Clear? Now, what are the properties of a cross product? We have the distributive properties. We have that the cross product of a vector times itself is 0 because the sine of the angle is 0 because we have 0 angle between the same vector, between a vector and itself. And this is interesting, is called anticommutative property. And it says that A cross B is equal to minus B cross A. So if we swap the order, as I said, the order matters of the two terms, then you need to put a minus sign in front. Nothing changes for a scalar. You can either have a scalar at the beginning, in the middle, or factor it out. And as I said, the order matters, so you cannot do these two left-hand side and right-hand side of this equation are not the same. So you need to decide which cross product do before. Okay. Then another concept we will cover a lot is first we will define the gradient. Do you remember how the gradient is defined and of a function? First, to define a gradient, you need a multivariate function, so a function whose domain is more than one variable. Otherwise, you have a derivative. And the gradient is the equivalent of the derivative for this multivariate function, and is a column vector. The fact that it's a column vector is just something, a convention. It's not really important. So the function is on, in this case, on n variables, and so the domain of the function should be on Rn, while the codomain is a scalar. So the output is a scalar of this function. The domain is monodimensional, is on R. And in this case, the gradient is the partial derivative of the function with respect to the first coordinate of the domain, and then with respect to the second, to the third, and then finally to the last one. So it's a column vector of numbers. Like the derivative, the gradient should be evaluated in some point. So you could have different values for different values of the domains of the domain. And the Jacobian is the same as the gradient, but extended into the case of a function that is not a monodimensional codomain, but is a m-dimensional codomain. So it's a m times n matrix with the entry j I j. Sorry, the Jacobian is defined with a capital J letter, is the partial derivative of the component fi with respect to the variable xj. So if you want to show this, you can see f as as a vector of numbers if you evaluate in 1 point, and you do the partial derivative with respect to the sorry, this is wrong. So yeah, yeah. So yeah, this is not correct. I will correct in the slides. So this is the right expression. It's we do the partial derivative of the first of the f1 function with respect to the first variable of the domain, and so on. And we have the first. Let's say this is, for example, the vector of an example of the and effector position, which is a function of the joint variables q. So the first coordinate of the and effector position, let's say the x coordinate, it's here, and we need to differentiate with respect to the first joint variable, and then to the second, and to the last joint variable, and then we have the second coordinate of the end effector, for example, the y direction, and we need to differentiate with respect to the joint variables. So yeah, no, that was correct. So what was wrong was like this. Sorry about that. Yeah, that's why it was not okay. So sorry, the first coordinate of the, for example, the end effector, you differentiate with respect to the first joint variable, then to the second one, to the third one, to the last one. And the second coordinate of the end effector, again, we differentiate about the joint coordinates, and the third coordinate of the end effector, we differentiate about the all the joint coordinates as well. But we will see this with numerical examples when we need to compute that. Then, yeah, for example, in the case of a function that is very simple, like this way, a linear function defined as matrix A times X, and we want to get the Jacobian of this function. We see that the Jacobian itself corresponds with the matrix A, because if we do the partial derivative of f with respect to the f1 component with respect to x1, we get A11, which is the first element of the matrix, and so on. Then another point is the chain differentiation rule. Let's think we have a function f defined from Rn where x live to Rm where y live. Then we define another function z, another function g, that has an output z and an input y, and is defined in this way, from Rm, because it has input y, and to Rp, so a p-dimensional space where z lives. And if we do the composition of these two functions, we can say, since z is equal to g of y, we can say that z is also equal to g of f of x, and we can define the composition function this way, and this composition function will be mapping vectors from Rn to Rp. And if we do the differentiation with respect to x of z, then we can do this way. So we differentiate first z with respect to y, and then we differentiate y with respect to x. And you see that these two, they can be eliminated and get the same result. This is quite useful. We will use that a lot. More complex cases, whenever the g function depends not only on y but also on x itself. And in this case, you have need to do you have a Cartesian product, so you have inputs from two sets, x from Rn, sorry, y from Rm, and this produces outputs in a p-dimensional space where z lives. And in this case, if you do the differentiations, you need to differentiate for the variables involved that are both the x and y. And if you differentiate first about x, you get the first term, and then you differentiate about y. But again, since also y depends on x, you have the other term as before. Then there are some also trigonometric formulas that are that we will use, that are the sum and addition formulas. And this relate, for example, the sine of a sum of or difference of angle to the product of the sine of the cosine of the angles considered in a separate way. And this is the sine formula, and this is the cosine formula. Watch out that in the sine formula, the minus here is the same as as in this case, while in this case they are opposite. So a minus here correspond to a plus here, and the other way around. Okay. So now that we did this introduction, let's go to the to start to define what a reference frame is, which is also called a coordinate system. And a reference frame is a tuple, which is a set that comprehends the OA, which is an origin, and three axes that are XA, YA, ZA. So we are talking now about frame A, so we give to the axis the same name of the frame. And so 4 elements, 1 origin and 3 axes, and we consider only right-handed frames. This means that these properties should hold between the axes. Cross product of XA times YA is equal to ZA. And this is how a reference frame looks like. And important point is that the axes are always perpendicular each other. Okay. Now let's do a little digression to distinguish between geometrical and physical vectors. So in our space, we say we have a vector space. We have vectors, but we can use vectors to represent both geometrical points and physical quantities. When we talk about geometrical points, we consider, for example, the position of a point in a rigid body, the vertex of a polygon. And these vectors that describe geometrical points, they are called geometrical vectors. And you can see here, for example, the same point P that it's in in R3, it can be represented in two different frames via two geometrical vectors, namely PA if you want to represent in the frame A, or PB if you want to represent in the frame B. You see these two frames have different origins and also a different orientation. So a geometrical vector is the representation of a point P that exists independently of the reference frame. The point P or exists as an entity alone itself. Then we want to represent either in a frame or in another. And when we do the representation of this point in a frame, it happens to give us a set of numbers, in this case, 3 numbers that are the coordinates. So the representation of the geometrical point depends on the reference frame. For example, in this case, we have one representation from frame I and one representation from frame B. And PA, for example, this represents a directed segment between the origin of frame A to the point. And the subscript A represent the frame where this directed segment is expressed, in this case, frame A. As I said, an example of a geometrical vector, the position of a point in space. We have point P, and we see that this representation, as I said, this P is a geometric entity independent from the choice of the frame, while PA is the representation in the frame A. And this representation is a set of 3 numbers that are called coordinates. So we project this in 3 on the axis of the frame, and we get the coordinates. While PA represents the distance from the origin, OA. Also. And it's a vector that has a magnitude, a norm, and a direction. And these 3 are the Cartesian coordinates because we choose a Cartesian frame with perpendicular axis, but we could also define cylindrical coordinate equivalently. In that case, we will use we will define everything in a different way. But let's just don't think about Cartesian cylindrical coordinate and stick to Cartesian ones. The other thing that you can represent with vectors are physical quantities. And physical quantities, for example, are linear angular velocities, accelerations, forces, and moments. And these physical quantities are represented by physical vectors that, again, they have magnitude, direction, and an application point Q. So depending on Q, if this application point has some physical or not has some physical meaning, we can distinguish between free vectors and applied vectors. A free vector is a vector for which the application point doesn't have any meaning. So you can move it around and will represent the same thing. Think about, for example, the velocity of a point. you can represent it with a vector, and you can put this vector wherever you want without changing the meaning of the vector. While in the case, so you see here these two vectors, this one and this one, they are the same. And also this one and this one are the same vectors, and their application point doesn't matter. But if the change of the application point affects the physical effect that produces the physical quantity, then we are talking about applied vector. Think about, for example, to a force acting on a rigid body. If we change the application point, in this case, let's say you're considering application point here, and you want to move it here, the moment about the center of mass, it's bigger in this case than this case and changes. So unless you're not just considering translational motions, then F is an applied force, applied vector. While if you're only interested in translational motion, then you don't talk about moments anymore, and you can define F as a free vector. Okay. Then what is the pose of a rigid body? Because till now we define about points, but a rigid body, to represent a rigid body, we need two things. First, what we want to represent. We want to represent position and orientation. And this is called pose. Pose is both something that represents both position and orientation of a rigid body. And to represent a pose, we need the position of one of the point of the rigid body, and usually we choose the center of mass point, and the orientation of the rigid body that we can represent with a frame. So here we have a rigid body. We have a frame ZA, YA and XA that we call frame A with this axis, and we want to represent the orientation of a rigid body with respect to this frame. So to do so, we attach a frame to the body. Attaching a frame to the body means that it's rigidly attached to the body, moves the body, but it's not necessarily inside the body. We could put a reference frame even outside the body. The important is that it moves with the body. So we attach the system to the body with its own axis, its origin, and axis XB, YB, ZB, and we describe orientation of this frame with respect to the fixed frame A. And we forget forever about the rigid body because we did only the one point and the that we consider the origin located, for example, at the center of mass of rigid body, and the frame that moves with the rigid body. Then to represent the orientation, we said we have different ways of representing orientation, and the first one we see is the rotation matrix. We will see why we will call rotation matrix afterwards. And rotation matrix is defined this way. We have the free axis. The rotation matrix, this is a rotation matrix that represent the orientation of a frame B with respect to the frame A. So let's say the frame B is the one attached to the body, and the frame A is the inertial one, the fixed one with the lab. And the columns of this rotation matrix are the unit axis So again, you see here we have talking about unit vector with unit norm of frame B expressed in frame A. Expressed means projected onto frame A axis. And we have three different interpretations of a rotation matrix. And the first one we will see is the considering the rotation matrix, the representation of the orientation of a frame, in this case of the frame B with respect to the frame A. And a rotation matrix is a matrix 3 times 3, so 9 entries in the 3D space. In 2D, it's only 2 times 2, so 4 entries. And the second property is that this peculiar 3 times 3 matrix, it's orthonormal. What does it mean orthonormal? It means that it's orthogonal. So the columns of the matrix, so the axis that represent the axis of the frame, you remember we were talking about orthogonal axis, are orthogonal each other. So the fact that the axes are orthogonal, it's represented, encoded in these properties that are the orthogonality. And the orthogonality, to define orthogonality, we saw that we can use the scalar product. So we have axis X and axis Y. And to say that Y is orthogonal to X, we do the dot product or the scalar product, that is the norm of the two vectors times the cosine of the angle between. Since the norm are unitary, it's 1 because they are talking about unit axis, then the cosine is, we enforcing that the cosine is 0, it means that the two vectors are orthogonal. Because cosine is 1 whenever the vectors are parallel and 0 whenever they get orthogonal. Sorry, the angle, the cosine is 0 whenever the vector are parallel and the angle is 0, and it's 1 whenever they are the angle is 90 degrees. So sorry, whenever the vector are parallel, the cosine is 1 and of the angle, and whenever they are perpendicular, the cosine is 0. And this is the orthogonal part, but we say orthonormal, so we need the normal part that exactly is what we said, that these axes are unit vector. So we can use again a property we saw for the scalar product, that if you do the scalar product of a vector from itself, you get the squared of the norm. And to say that the unit vector, we say that the scalar product of each axis by itself is 1. And so we have 1, 2, 3, 4, 5, 6 properties. And these are encoded with the following results. So the inverse for an orthonormal matrix, the inverse of the matrix corresponds with transpose. And this encodes all these 6 constraints that we saw. And you can, since the inverse times the matrix, it's the identity, you can also write this. And an important point is these constraints are 6, while we have nine entries. We have 9 numbers on the rotation matrix. This means that we could have used only 3 degrees of freedom to represent the orientation of the frame. So the rotation matrix is called a non-minimal representation because there are more than 3 degrees of freedom. Okay. We will see in the next lecture that there is a minimal representation that uses only 3 numbers to represent orientation, but all these representations that are minimal, they suffer from the fact that there are singularities. So they cannot represent all the orientation. There are some orientation that you cannot do nothing. And you need to be aware about that. Otherwise, your robot will explode. In particular, for our legged robot, quadruped robot, we know what are the orientations that are not representable with this, for example, new representation is Euler angles. The third property is the fact that the determinant of a rotation matrix is +1. It's 1, and this means that we are considering proper rotations. Proper rotation means that a positive rotation is counterclockwise with respect to the rotation axis. We will see this in the next chapter. What does it mean? So every time you have a rotation matrix, you need to be sure that you have all these properties satisfied, and you need to check them. For example, let's do an example. We have a matrix this way. In this case, the axes are unitary vector, so the second property, the normal property is satisfied. And you can see that these vectors are the basic vectors of and are perpendicular, orthogonal each other. And the missing property is that you want to compute the determinant of this matrix and see if it is 1. So we use the Saros rule, which allows us to compute the determinant for a 3 by 3 matrix, just replicating the first 2 columns. And then we do this multiplication, 0 plus 0 plus 0 minus this other multiplication, 0 I did something wrong. Yeah, the last one, sorry, I copied wrongly from the previous one. And this one, which is -1. So determinant is -1, and this is not a rotation matrix. So be very careful whenever you check this. Now let's have a better look at how the rotation matrix is defined. We said that is the matrix ARB, it's represented orientation of frame B, and that the column of this matrix are the axis of the frame B projected onto the axis of frame A. So again, we can see here as using the cross product, dot product idea, that we have the 3 axes of frame A, and we project first the x axis of frame B, and we project it onto the x-axis of frame A. Then we project it onto the y-axis of frame A, and then onto the z-axis. And the same for the y and z-axis. Now, if you remember the formula of the scalar product, because we have unitary axis here, we have that this projection is just the cosine of the angle between the two axes. This way, because of this reason, the column of the rotation matrix are called direction cosines, and these are the direction cosines of the ZB axis with respect to the frame A axis. These are the direction cosines of the y-axis with respect to the frame A axis, and these are the direction cosines of the x-axis of frame B with respect to the frame A axis. So this is just a notation. Everything is clear?
Yes.
Now let's see an example. We have a frame A that looks like this, and we want to define the orientation. We want to draw frame B that is represented by this, whose orientation is represented by this rotation matrix with respect to the frame A. So how does it looks like? First, we can inspect the columns and look, for example, if we look at the z-axis of frame B, what can we know from these numbers? We say that these are the projection with respect to x-axis of a frame A, y-axis, and z-axis from frame A. So first we have zeros, both here and here. So we know that ZB it's orthogonal to XA and ZA. And because we have one here, we know that is aligned. So its projection is 1, means that is aligned with YA. Okay, so we draw this. ZB is aligned with YA. ZA, okay, ZB. So we draw it here. Then whatever we see here, we see here that the projections, this is YB axis projected on A. So we see that the projection, so the YB axis is perpendicular to both YA and ZA, and that is aligned with XA but it's not really aligned, it's opposite to XA. Opposite to XA. You will have the slides properly written whenever they are uploaded. So opposite to XA, I draw YB this way, opposite to XA. And then the third one, we see this is XB projected in the frame A, and again we have perpendicularity with respect to XA and perpendicularity with respect to YA, and is opposite to ZA. So we take ZA and we draw it opposite, and we have drawn the frame B. And an important point is that to know frame B, you don't need only the matrix RAB of numbers, but you need to know also how is frame A. So it's not the matrix of number is just a rotational matrix with some properties, orthonormal matrix. But to be able to draw the end frame, you need to know the start frame as well. Everything is clear? Now, let's talk about composition of rotations. Let's think we have a matrix RAB that represents the orientation of a frame B with respect to a frame A. And a matrix RBC that represents the orientation of a frame C with respect to a frame a frame B. Now, if we can compose this rotation to find a representation of orientation of frame C with respect to frame A. And to compose the rotation, we just multiply them together. So you see, I will redraw this. It's okay, it's already written as you see. You compose first the rotation, the orientation of frame B. So from a frame A, we want to represent frame B. And then from frame B, we move to frame C. And we see here that these two cancel out, and we have the orientation of frame C with respect to frame A. And note that the product of rotation matrix is not commutative. So if you swap the order of these two, you still get a rotation matrix, but you don't get a rotation matrix that goes from A to C. It could be whatever one, another one that still is a rotation matrix, but it doesn't mean that doesn't have the same meaning. And this is because the composition of rotation is not commutative. You cannot swap the order. So if you do a rotation and then another one, it could be different than doing the other one and then the first one. This is a very important point. Oh, sorry, I will. Okay. Then the rotation matrix inverse. How do we find the inverse of a rotation? The inverse of a rotation matrix is just swapping the two frames. So if you have a rotation matrix ARB that represents the orientation of B with respect to A, the inverse of this, it's the matrix RBA that represents the orientation of the frame A with respect to the frame B. And we saw that because these matrices are so you could see, if you compose these rotations, you could see that these two cancel out, and we remain with a rotation matrix from A to A, which is just the identity. So there is no rotation at all. And because we are talking about rotation matrix, we saw that the inverse is equal to the transpose, and we can write this way. The inverse of this is swapping the two frames, because a matrix times its inverse its identity, right, for the definition of inverse. So this holds. We can say that if we think about the rotation matrix as an element of a group, the rotation matrix, they form a group that is called spatial orthogonal group of dimension 3, SO3. And spatial because you have determinant equal to 1, and orthogonal because of its orthonormal properties. And to define a group, we need to we have three properties that needs to hold at least, and one is that the product of the element of the group, in this case we have the composition of the matrix, is still an element of the group, and we saw that because if you compose two matrices, you still get a rotation matrix, so it doesn't get out from the group. Then exists a neutral element that means that if you multiply the element of the group for this neutral element, you still get the same element of the group, and this role is represented by the identity matrix. And you have also an inverse element, which is for any element of the group with this, if you multiply by this inverse element, you get the neutral element, and this is represented by the transpose, which is the inverse of the matrix. So inverse of a matrix is the transpose of a rotation matrix, and you swap the frames destination and origin of the original one. The second interpretation. So we can do the break here. 10 minutes and continue with the next part, because this is a new interpretation of the rotation matrix. If you have any question till now, you can ask. Let's continue. Now, the second representation of a rotation matrix is the change of coordinates. So you can interpret the rotation matrix as an operator that changes coordinates of a vector. So assume, for example, that the point P doesn't move, and we have the coordinate related to the reference frame FA, represented by the black dots. We can see IRB as a linear operator that maps a vector from the frame B to the frame A. So this is the second interpretation. So we want to, let's assume that the P vector is expressed in the frame B from the green dots, and the rotation matrix ARB, it's mapping this vector into a frame A, finding out the coordinates with respect to frame A that are represented by the black dots. So to understand that, let's first rewrite PA differently. So we said that PA are the coordinates of P with respect to frame A, which are the black dots. And we can rewrite the same thing, pre-multiplying by the identity matrix. We know the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Then the matrix product for a vector, we can rewrite this way: 1, 0, 0, P xa, this is a scalar, plus this, another scalar, and the third component, the third coordinate, this way. Now these are the axis of frame A with respect to frame A. Okay. Now, if we have the coordinates of P with respect to frame B, which are the green ones, and we want to get the coordinate with respect to frame A, we need to find a set of new numbers. So we use the rotation matrix that represents the axis of frame B in frame A, expressed in frame A. And we multiply for the coordinate that we have of P expressed in frame B. And this is PB. So these are the three axes. Unit axis with a hat. Each one multiply for the corresponding coordinate. Right? So I get the green dots, for example, about axis xb, and then I multiply this axis xb for the scalar representing the coordinate along the axis xb, and I get the vector expressed in frame A. So we can see the matrix ARB that performs a change of coordinates of vector P from the frame B, which are the green dots, to the frame A that are the black dots. While to get the opposite, we rewrite the same formula as before, and to get the green dots from the black dots, so the coordinates in frame B of the same vector, starting from the coordinates in frame A, we do the inverse of the rotation matrix. And we know that this inverse is equal to the transpose and is equal to the rotation matrix where we swap the two frames. And you see that this is meaningful because we have that PA is multiplied by the it's transformed into the B frame using this rotation matrix. You see these two should be the same, and we get PB in essence. Is it clear? Now let's do a quick exercise. We have a vector expressed in the B frame that has these three numbers, 1, 1, 1. Let's say this is the reading of our force sensors, and we want to map it into the A frame. And we know that the rotation matrix ARB has this shape. First, we want to check if the IRB is a rotation matrix, so we want to check if the column are unit vectors, so the normality. And we see the first column, for example, it's if we do the square of the component to get the norm, we get 1/2, and we see that this is +1 +3, 6/6 is 1. Second one, it's square of first component plus 4 square of the second one plus 1, 6. And again, we get 2 plus 4 plus 1 This is unitary as well. And the third one is 1/3 plus 1/6 plus 1/2. And this is 6 divided by 3, 2 plus 1 plus 3. And again, we have unit square norm and unitary vector. Then orthogonality. We can see that we can do the scalar product of this and this and see if it is 0. So we have 1/3 plus second component is minus 2/6, and the third one yeah, this is 1/3 minus 1/3 equal to 0. And you can check this for the other combination of column and also for the determinant. It should be equal to 1. I'll let you do this as an exercise. And what we want to do now is to compute the values, the numbers of the numbers that present the coordinates in the A-frame. And this is done by multiplying the PB for the rotation matrix that changes the coordinates with respect to A-frame. So I can rewrite the rotation matrix here. This was PB. And if we do the multiplication, we see here that multiplying by this vector is just summing up the component, this, and this for the first element. And we get 3 divided by square root of 3. If we sum up these 3, we get 0. And if we sum up these 2, we get 0 again. So what can we say about frame A? First, we can say that P, the point P, it's along XA. Because the other two components are 0. So the frame A has XA located along the vector between the origin and the point P. So in here, we are considering the origin of the frame coincidence. So whenever we are changing coordinates, we just assume the two frames share the same origin. Then the second thing we can say it's that if we look at the matrix, here we have a 0, And this means that you remember this is the column related to the YB axis. It's orthogonal to ZA because this projection is 0. And the other thing we can look, for example, here, this is a positive number. So the projection of the XB axis, that is the one related to this column, it's positive along what? Along ZA. And finally, YA should form a right-handed frame with the other two. And if we draw that, we said that XA, it's along, P is along XA, Y B is perpendicular to YA, so this is a perpendicular vector. Sorry, YA is perpendicular to YB is perpendicular to ZA. Sorry, this is ZA, and XB is positive along ZA. So between these two axes, between all the axes that are perpendicular to YB, we get this one, and YA is to form a right-handed frame for which the cross product between X and Y it's Z. Yeah, this is just an example to exemplify this changeless coordinate property of the rotation matrix. Then we can consider, for example, elementary rotations. Elementary rotations are rotations that are defined with respect only to one axis. Again, let's consider we have two frames with the common origin, FA and FB, and we have the frame FB rotated of an angle phi with respect to the frame A, and we have the point P expressed in the B frame with these coordinates. Now, let's consider one rotation about the z-axis. So we have a planar rotations here, and we consider only the that the u and v coordinate are changing while the last one is fixed. So think about a rotation about an axis that is coming out from the paper. And if we have PB, we can get PA, so the projection, the coordinates of P with respect to the frame A with some elementary trigonometry. So let's call, again, let's say the coordinate on the z-axis are the same, so z equal to w, and the coordinate x and y could be expressed this way. X is the segment OB minus the segment XB, and OB could be expressed as U cosine of phi minus the segment XB could be written as V. So this angle phi is the same as this. So we have V sine of this. We get this segment that is XB. And for the Y component here, we get OC with a second OC plus CY. There's an error in the slide. Which is this segment OC, which is U sine of this angle, plus this segment, which is V cosine of this angle. Now, if we reorganize this free coordinates expression in a matrix form, we get, sorry, X, Y, Z represent the coordinate of P in frame A, and we get cosine of phi. So we have the coordinate of P in B here, U, V, W. We said that Z coordinate it's equal to W, so we put 0, 1, 1 here, and we get cos phi minus sin phi and sin phi cosine of phi, and nothing for this. And this is what we call the elementary rotation about the z-axis, as this expression. We call it Rz of phi, because we rotate about the z-axis of an angle phi. And we can see that this is the z-axis of frame B and A that are coincident. This sorry, PowerPoint got stuck. Okay. A directional cosine of XB axis about frame A, and this I don't have the color, but let's just a directional cosine of YB of y-axis of frame B about frame A. Now, yeah, what if instead of a rotation of an angle phi, I want to do a rotation of an angle minus phi? How does it look like? So an elementary rotation of an opposite angle, it's the transpose. And this is because if I rotate, if RZ represent the rotation of frame A to get frame B of an angle phi, then to get to rotate, if you rotate FB of an angle minus phi, I get frame A. So it's just the inverse of the elementary rotation that is represented by the transpose. You can do as an exercise the derivation of the elementary rotations about the x and y axis. You see that we use different names for the angles. And this is on purpose because we will see later on that these are called Euler angles and represent roll pitch jaw angles in our representation of orientation that we will explain next lecture. Pay attention that the minus sign is here, but here is here, so they are not. You need to derive yourself to be sure you don't do any error. Everything is clear till now?
Yes.
Then the last interpretation of the rotation matrix, it's the one that consider rotation matrix a way to rotate a vector inside a frame. So an operator on vector. So now let's think the frame is fixed. We have a vector v here. And if you apply a rotation matrix, we will get a rotated vector inside the same frame. Again, let's assume for simplicity that we do a rotation only around z, and we can express the coordinate of v plane here, because the z component will be the same this way. V is rotated of an angle alpha with respect to the x-axis. So, and with respect to the y-axis, we have the sign. And then if you do the same for vector v prime, we have x prime, y prime, and this will be the norm or the vector v, that because we rotated, the norm will be the same, and consider an angle alpha plus v. Okay, and the same for the y component. Okay, then using the formula that I showed you before, the sum and difference formula, trigonometric formula, we can express this cosine as a cos alpha sin phi minus sin alpha sin phi. And we can see here we can extrapolate the x component. We recognize it and we get x sin phi. And here we see the y component. And doing the same for the other one, we apply the formula for the sine, for the sum of sine, and is sin alpha cos phi minus plus, sorry, cos alpha sin phi, and then again we get x cos phi. You can work out, sorry, this is y cos phi, because it's v sin alpha, it's y cos phi plus v cos alpha x sin phi. And if we write this in a matrix form, again, we have sorry, this was cos phi. Cos phi minus y, we have sin phi in correspondence of y, and 0 for z. With z prime equal to z, because the rotation is only about the y-axis. And then here we have sin phi, cos phi, and 0 and 0. And we recognize here the elementary rotation that we just saw, which is a rotation about z of phi. So again, that's why we call the rotation matrix a rotation matrix and not an orientation matrix. And this thing is very used in graphic cards, and it's very fast operation because it's done on hardware. And whenever you change orientation in your view, all the points in the solid you are drawing should change over time. And that's why this computation should be done very fast, and is done on hardware. And this interpretation of a rotation matrix to rotate a vector inside the same frame holds for also for not only for this elementary rotation we just saw that gives the same results that we got before, but also for a generic rotation. In a summary, the free interpretation, a rotation matrix represents the orientation of a frame B with respect to another frame A. Can represent a change of coordinates of a vector from a rotated frame B to the original frame A. And also is an operator that rotates vector inside the same frame. Everything is clear? Now, another important result that we will use quite extensively is the derivative of a rotation matrix. To get the expression of the derivative of a rotation matrix, we start from the property of orthogonality of a rotation matrix. That it's this one that is equal to inverse equal to the transpose. So this is the transpose is an inverse. So it's equal to the identity. If we differentiate this with respect to time, we get something like this. The derivative of the first is a product of two elements. So derivative of the first times the second plus the second plus the first times the derivative of the second, the product of product rule. And what is the derivative with respect to time of an identity matrix? Identity matrix is always constant. It's as this.
It's 0.
It's 0. So we have something like this. And here we see, if we call this term S, we see that we have a matrix that this is a transpose of S, a matrix that sum to this, to its transpose is giving 0. And we saw this before, how it's called this matrix S is skew symmetric. So S is a skew symmetric matrix. But how does it look like? So for now, oh my God. Yeah, I would rather write everything. Let's consider this S equal to R dot R AB transpose. So we can define our derivative, that is what we want to know, in terms of this S. So we multiply both term by R, and this one will cancel out. We get only the derivative, and we have the other one that is like this. And to see how S looks like, we need to consider, for example, constant vector in a rotating frame B. So let's think we have a rotating frame B. That rotates with respect to a frame A that is fixed, and we have a constant vector P that doesn't move, so it moves together with the frame B. And we saw from before that we can express a constant vector in frame B thanks to the rotation matrix in frame A. Okay. Now, if we take the velocity, do the time derivative of this vector A, we get again the derivative of the rotation matrix times PB plus the rotation matrix itself, first term, times PB dot. But we say this is constant, so it's moving with the frame B, but not getting far or closer from the origin of frame B. So its derivative with time is 0. We can cancel out this term, and we get this. Now, and we, from mechanics, we know that the velocity of a point in a rotating frame, it's omega expressed in the same frame A cross, which is the cross product, the vector PA. And this comes from physics. And now we can equate these two expression, this one in this one. And from here, from before, we know that this derivative of rotation matrix was the S matrix times R AB PB, which is nothing else. So if we equate these two expression, we get omega A cross PA. Sorry. Yeah, sorry. This is PA because we map PB through R, and this is equal to this. And we said that from before R dot equal to S R A B, and if you work out the computation, you get this expression as R A B equal to omega cross R A B. So the derivative of rotation matrix, it's the angular velocity cross product the rotation matrix itself. And we saw that we can express this cross product as a matrix product using the skew symmetric matrix associated to the cross product. So we build up the skew symmetric matrix this way, and we have an expression for the derivative that is equivalent. Anyway, we will look. You will see this development in the slide, properly done, and to finally to better define the properties of a skew symmetric matrix. It's a square matrix, as is the matrix is equal to minus its transpose, which means that you have off diagonal term oppose each other and zeros on the diagonal. And also another property of the skew symmetric matrix is that if you put them in a quadratic form, this way, you will have always 0 for any vector you put in X. And the canonical form of a skew symmetric matrix, it's this one. So you remember you have the Z component here, the opposite one here, the Y component here, an opposite one here, and this is for the X. And X is expressed this way, the one associated to the cross product. And so the skew symmetric matrix associated to the cross product, we saw these properties before, but you also can have a rotation of the vector A inside the skew symmetric matrix. In this case, the rotation comes out and get pre and post multiply this way. Again, as in the case of the cross product, if you swap these two, you get a minus here. So this is another property, and this is a property that relates the multiplication of two skew symmetric matrix associated to the cross product to the this that is the outer product, and this that is the norm. So an outer product is a matrix, is a vector times its transpose, while the norm, which is the transpose of a vector times itself, it's just a scalar. So we multiply for the identity matrix. So this is just an expression we use later on, and to connect the skew symmetric matrix with the symmetric matrix, we have that the symmetric matrix has not a minus, so the matrix is equal to its transpose. And if you put it in a quadratic form this way, you have that this is always different than 0 for any vector that is non-zero. So it's something, if you are representing this with a function, is something that has a 0 here and is always positive. And the important thing is that a symmetric matrix has real eigenvalues, and you can always write a generic matrix as a sum of a symmetric part and a skew symmetric part. So you can check that if this the matrix A is just that the sum of these two is just the matrix A, because you have A transpose divided by 2 plus A divided by 2 minus A transpose divided by 2, and this is equal to A. So this, you can always split a matrix in a symmetric part and a skew symmetric part in this way. And a positive definite matrix is a special kind of symmetric matrix where the eigenvalues are not only real but also positive. And if you put it in a quadratic form, you have that is always positive. While this one, so this is the case, sorry, of a positive definite matrix. While for a symmetric, you could also have a negative definite matrix, or something that is touching the 0 and 1 point, and it's positive or negative. Yeah, so for today, I think we are done. If you have any question, let me know. Otherwise, next time we continue with Euler angles, exponential maps, and quaternions, and we start to address the real kinematics of a rigid body using this representation of orientation we just explained. I will put some exercises also in MATLAB in the folder of labs. There is a kinematic lab that will be you can try different exercises and examples in this M file that I will create in MATLAB. And another point is that for the ones that got some issues in downloading the new virtual machine, you can write an email to Octavio to tell him about that, and we'll send you a link on a Google Drive, or we will update the link Dropbox with the Google Drive one. We'll see. We'll put both for people that didn't manage to download the virtual machine. Okay, so if there's not any question, see you next week, Monday, and I will upload as soon as I have them ready, the new slides for you to follow. And try to download the latest version, because I always spot some typos because the slides are new. And have a good evening.
Thank you. Bye.
Bye bye.